Question number 7. Isomers X and Y have the molecular formula C5H8O. Give the name for isomer X. Well, let's have a look at it. It's got single bonds. It's got 1, 2, 3, 4, 5. It's pentane, but it's cyclic. So it's cyclopentane with a ketone group, a carbon double bonded to an oxygen. So cyclopentaneone, but I need to drop the E so I don't have an E and an O of the one together. Cyclopentaneone. Explain how X and Y can be distinguished in terms of boiling points. Well, boiling points are due to the intermolecular bonds. The carbon to oxygen here is going to be a polar bond. So oxygen is more electronegative than the carbon. So the oxygen is going to have, it's also got lone pairs of electrons, it's going to have a slight delta minus, and the C has got a slight delta plus. And so those delta plus and delta minuses between the different molecules will attract as an intermolecular bond. A carbon to an oxygen, or a carbon to a Cl, or a carbon to a Br, that forms dipole-dipole attractions. However, if I've got an oxygen to a hydrogen, or a nitrogen bonded to a hydrogen, or a fluorine bonded to a hydrogen, the difference in electronegativities between the oxygen and the hydrogen, or the nitrogen, the hydrogen, fluorine and hydrogen, is very much larger. So oxygen gets a very large delta minus, and H gets a very large delta plus, and so the intermolecular bonds between these polar bonds in the molecule and the polar bonds in a neighbouring molecule, this hydrogen bond here is much stronger, so this is going to have a higher boiling point. So Y has the higher boiling point because Y has hydrogen bonds and X only has dipole-dipole intermolecular bonds, and more energy is needed to overcome these hydrogen bonds. That's why it has a higher boiling point. Carbon-13 NMR. I've got one carbon environment here at the top where the CO is. These two are symmetrical. We've got a line of symmetry right down the middle, so this would give a second peak, and these two would give a third peak. These in the same environment. Same for this. One carbon environment bonded to the C, bonded to the OH. Another carbon environment because these two are symmetrically opposite, and a third carbon environment for these two which are symmetrically opposite. So they're both going to give 3 peaks. However, they'll have different shift patterns, so the peaks will appear along the x-axis at different points. So they've both got 3 peaks in their carbon NMR, but then if we look in the data book, a C double bond O to a C, so there's a C there and there's a C here, a C double bond O to a C. This carbon here, look at the carbon that's bold, this carbon bonded to a CO, so this one here or this one here, both given the same peak, remember, is going to have a peak with a shift pattern of 20 to 50. Okay, this one doesn't have any C's bonded to COs, but it has a C bonded to an O bonded to an H. So this C here and this C here are bonded, sorry, this C here at the top, rather, this C here, which is bonded to an O, this C here at the top is bonded to an O, and it's an alcohol, so that would give a peak between 50 and 90. So these two carbons here would give a peak with a shift number of 20 to 50. This carbon here bonded to an O in an alcohol would give a peak with a shift value of 50 to 90. And then finally, the infrared spectra. I've got a carbon to oxygen bond, and I've got a carbon to OH bond here. So I've got a C double bond O, and I've got a C OH here. So if I look here, a C double bond O gives an absorption in the infrared spectrum of 1680 to 1750. Important you quote that. Quote it from the data book, write it down from the data book, and Y as an OH, which is going to give an absorption at 3230 to 3550. Again, write it down. And you might as well say they're both going to have different fingerprint regions. That's the sort of messy region below a wave number of 1500 centimeters to the -1. So it's the right hand side of the graph, and that messy value identifies the compound. So if you're not exactly sure what it is, you get a known sample of what you think it is, you run it through the infrared spectrometer, and if it then gives the same fingerprint pattern, you know that you've got your sample and your unknown sample are the same. So your known sample and unknown must be the same if the fingerprint region below 1500 is the same.